All right, so here's one of those special cases you'll probably just want to memorize if your teacher covers these. And most teachers will cover circles. Usually they'll put in ellipses. Hyperbolas are pretty unusual in such a special case that you might not see them. But here we go. All right, so first of all, I just want to throw the equations at you. And then, because maybe you'll want to back up the video and refer to this during your homework or something. And then we'll get into a few example problems just to show you how to use them. We'll just point out some little details about this. So first of all, very often, a circle or an ellipse is not centered at the origin. It's like up here at 2, 3 or whatever. So we just call that center h, k. H comes before k in the alphabet, so that's how you remember which one's h and which one's k. So the x coordinate is h, y coordinate is k. And that's why you're always going to see h's in the x equations and k's in the y's. Alright, so that's the first thing to notice. Just like with the rectangular equations of ellipses and circles, h and k just kind of get added in there in order to shift this thing up and around. The slight difference is that in the equation of a rectangular equation, a circle, if a circle were entered it would have an x minus h squared. And there was that, what I want to remind you of is that there's that h, x minus h right here. So if the center of a circle was at x equals 2, you're going to have x minus 2 squared in parentheses, because that's just the way it works. You do the opposite of the x coordinate. But in these equations, there is no negative in front of the h. So that's just a little subtlety. That actually makes these easier. I just wanted to point it out so you don't get confused. In the rectangular versions, we're going to have negative signs in front of the coordinates, basically take their opposites. But in their parametric equivalent, we're just going to have a positive h and a positive k. But other than that, if the thing is centered at 0, 0, for example, all the h's and k's go away. And you just end up with r cosine theta for x and r sine theta for y. Now what's the difference between a circle and an ellipse? They're basically just the same thing. A circle is a special case of an ellipse where a and b are the major and minor axes. You might recall them being called in a previous class. The minor and major axes are identical in a circle. But in an ellipse, a and b are what they call basically the width and the height of the ellipse. And one subtlety is I've given you the equations right here, and I have a on the x equation and b in the y equation. It doesn't matter. You could switch a and b. But the point is that whichever one of these coordinates has the cosine is usually an x coordinate for an ellipse. And then the number in front of it just sort of tells you the width of the ellipse from the center. So the width of the ellipse is actually going to be 2a. And then whatever's in front of whatever's in the y equation, like this b here in front of sine, that's going to be the height of the ellipse. And the overall height of the ellipse will actually be 2b, and its width will be 2a. And that's just because a is actually the distance from here, from the center to the edge, and b is the height from the center to the top. So that's why the overall height would be 2a or 2b. And hyperbola, very similar looking equation, except we switch cosine and sine out and put secant and tangent instead. Seems like a lot of classes don't cover hyperbolas. They're sort of pointless anyway, so alright. Let's take a look. How do we convert this circle to parametric? Now, as I showed in the previous video, we could say, oh hey, x equals t, and therefore solve and get some crazy square root stuff. But I would recommend just memorizing this. So this is just here as a reminder for the generic equation of a circle. So just looking at this equation, because there's no parentheses, I know this is a circle centered at 0, 0. And I know its radius equals 2. That's the one way to screw these up, is to not remember that the number over here is r squared. So you got to take the square root to get the radius. And now we're just going to plug and chug. So x equals h, which is 0 in this case, plus the radius times cosine theta. And y equals the same thing, only sine theta. Alright, so it's that easy. If you recognize you're dealing with a circle, just pick out some key information, plug it into the formulas you memorized, and you're set. Going backwards, so here's another circle, only this time it's parametric, and we want to convert it to rectangular. So what do we notice right away? How do I know we're dealing with an ellipse or a circle and not an ellipse? It's because the 4 in both cases. So because the a and the b match, we have the same number in front of both, that means we're dealing with a circle. So what is its radius? Well, r is just the number that's in front of the sine and cosine, so that's a 4. And then the center of this thing is at that coordinate, and that other one. So 2 comma negative 3 is the center. And we'll just plug and chug through the standard equation of a circle, which is x minus h squared plus y minus k squared equals r squared. So that is x minus 2 squared, y minus the y coordinate, so that's plus 3 squared, equals r squared, which is 16. Alright, isn't that wonderful? As long as you spot your equation, pick the key information out, you can just switch willy-nilly between parametric and rectangular. Alright, here's a slightly dicier one, looks kind of crazy. Here's a graph, it's obviously an ellipse, and they want us to find a parametric equation. Well, so first, in case we don't remember it, x is going to be h plus a cosine theta, and y is going to be k plus b cosine sine theta. So the question is, what's h and k, and what's a and b? So first of all, let's figure out what the center is. Looks like it's at the point 2 comma 3. And then, so I've got the center, so h and k. Now the question is, what is a and b? So far I've got x equals the x coordinate, which is 2 plus something cosine theta. And I've got that y equals 3, the y coordinate, plus something sine theta. So now I just need my a and my b, and I'll be done. So what goes in front of the cosine in the x equation is just the distance from here to here. And just counting that off, it looks like this is x coordinate 2, this is x coordinate 4, because it's above x equals 4. So that little distance is 2, just throw a 2 in there. And then this vertical distance is going to be b, from the center down to here, which it looks like is about 1. So just leave nothing in front of there, an imaginary 1, whatever. And that is our equation, parametric equation. We could also figure out the rectangular version of this equation. Again, if we just go back to the graph, we'll just have x minus the x coordinate squared plus y minus the y coordinate squared equals 1, but then the trick is that each one of these is divided by the little a or b squared. So since this was 2 in the x direction, that means I've got a 2 squared down here. And since this dimension is 1, I've got a 1 squared right there. That'd be the standard rectangular version of an ellipse. Alright, beware intervals. So what we mean by intervals is that they gave us a limitation. It's just from 0 to pi. Now what I've done here is I've given us the same 3 equations, and I've just put some different negative signs in, because that actually will mess with you in a parametric equation. So let's take a look. Now just by looking at it, it seems that we have an ellipse, because in all 3 of these pairs of equations, we've got a cosine and sine, just like usual, except we've got a 1 in front of the cosines, and we've got a 2 in front of the sines. So that means we have a tall and skinny ellipse. So the x-coordinates, and you can kind of see that since cosine goes from -1 to 1, our x-coordinate is going to go from -1 to 1, but our y-coordinate is going to go from -2 to 2, because there's sort of like an amplitude of 2 in front of the sine. So the question is, what happens as we go from 0 to pi? Do we get the top half of the ellipse, the right half, the left half? What do we get? Well, let's just by plugging in 0. Plug in 0 for cosine, you get 1, and you get 0, so 1 comma 0. Then if you plug in pi, you'd get -1 comma 0. Then the question is, do we go up over the top to get to there, or do we go underneath? And it looks like if we plug in pi over 2, which is halfway through the interval, we'll get positive coordinates. So, and we'll get a positive 0 comma 2. So go through this point. So the graph of the parametric ellipse, it's just the top half, and it's going this direction. Because as we go from smaller, from 0 to pi, so going from smaller numbers to bigger numbers, we work our way counterclockwise around that semi-ellipse, that half ellipse. So what's going to happen to this one? Looks like my x-coordinate, so once again we have the same interval, 0 to pi, and my x equation is exactly the same as last time. So my x's should go, if I plug in 0, I'll get 1. If I plug in pi, I'll get -1. So x is going to go from +1 to -1. But look at this -2. Sine that's just going to basically flip this thing over. We're just going to reflect it like this. If you wanted to, you could plug and chug though. So we'll get from this point to this point. If we plug in pi over 2 right in the middle of the interval, sine of pi over 2 is 1, but multiplied by -2, we get -2. So this point is in the arch. So the graph looks like it's a semi-ellipse again. But this time, it's going that way. Since we're going from, again, we're going to go in the direction as we plug in the parameter, it gets bigger and bigger. So if we start at 0, that's our starting point. Our ending point is at pi, which is right here. And as we work our way along the interval, we work our way around the ellipse, clockwise this time, semi-ellipse. All right, in this last one, we throw a negative in front of the cosine theta. So that means our starting point, when you plug in 0, you get -1 for x and 0 for y. Then when you plug in pi over 2, you get 0 for x and +2 for y. And then when you plug in pi, you get -1, which is +1, comma 0. So this time we get a graph that looks identical to the first one, except instead of the arrows going like this, they're going to go the other way. So we start down here and go this way along the curve. And like I said before, if you have one of those teachers who's a stickler for these little direction arrows, don't want to leave those off. That's the direction of the path, if your teacher's into calling these paths. All right, and last one we'll do here is a quick hyperbola. But like I said, these aren't super common. Most teachers don't do them because it's, I don't know, it's just kind of pointless. All right, so find the equation of the hyperbola, and I'm giving you the vertices. Now, there's not the easiest problem I could have asked. We could have said, hey, given you its center, given you its width and height and stuff, it's a and b. Because you'll notice we have an a and b here. But what do we do with a foci? What's that? Well, just as a reminder, a hyperbola, that's the one where you kind of drew a box and then put asymptotes like this, and then the hyperbola was like this. Kind of had two mirror halves. If you don't remember that, and your teacher's one of these ones doing hyperbolas, you probably want to go back and watch the Algebra 2 chapter on conics and just refresh yourself on the hyperbolas. But the point is that these foci in a hyperbola are out here. They're kind of like in a satellite dish or something. You got that little antenna sort of sitting right above the dish. That's the focus of the satellite dish, and that's what these are. So I just always, the way I remember where the foci are of a conic is, they're kind of like inside the curve. If they're inside an ellipse, but they're on the outside of a hyperbola. So out here, so they've just given us the coordinates that these are at the point 5, 0 and -5, 0. But then the vertices, which is right here, those are at 4, 0. So the question is, what are a and b? Well, it turns out that this distance right here, that's a. So right away, and we know this thing is centered at 0 because these foci and the vertices are both symmetrical about the origin. So it looks like the center of this thing is right at the origin. So that means I can just start plugging and chugging. X equals 0 plus something secant theta, and y equals 0 plus something tan theta. Now a, because it's a horizontal distance that they've given me to 4, 0, this distance right here is 4, so that means we have our a is 4. Our little x coordinate, our x stretch, is 4. So that goes in the x coordinate, the x equation right there. But the question is, what's the y coordinate? How tall is this little box, to give me the parabola, the hyperbola, sorry. So it turns out we have to figure that out with a little equation. And again, you may recall this, you might not. But in all these conics, there was always a relationship between a, b, and c. And it was in hyperbolas, it's a squared plus b squared equals c squared. In ellipses, it was opposite, so it was more like b squared equals a squared plus c squared or something. The way I remember is I just look at the graph, look at whichever one's biggest, and put it by itself on one side. So like since the foci are way outside the graph, they're bigger than a, and they're probably bigger than b. So that's how I know c squared goes by itself, and then the other two squared added up on the other side. But the point is, we got a squared plus b squared equals c squared. Since I know c is 5, and I know a was 4, I can solve pretty quick to get that b squared equals 25 minus 16, which is 9, so b equals 3. And that's how I get a 3 right here. But again, if you have one of these teachers who's actually going to do hyperbolas in parametric form, then you're just going to need to practice this a little bit. But honestly, even if you had that teacher, it's probably going to be more about ellipses and circles anyway, because they're a little bit more varied, a little bit more fun. So, there you go. Live it up. Love your parametric equations. But know that this stuff is kind of pointless. It'll come and go this one time. The exception is projectile motion. So I'm actually going to make that a separate chapter about projectile motion, which you'll be able to find in trigonometry. Probably drop it in here at the end of this chapter, and I'll probably give it its own heading in calculus, because projectile motion, man, different teachers throw that in different classes, but that is the classic example of parametric equations that actually do something. So it tends to pop up in various places, and that's why you'll find it in various places on this website.